thing is exactly like a determinant. This is a Jacobian factor, actually, of the reparameterization. And so when I, let me just skip ahead to the punchline here. So basically, if I take the integral written in terms of the other parameterization x, right, and then, goodness gracious, sorry. Oh, stars. Anyway, so getting back to the point. If I write the flux in terms of oh, goodness gracious, I'm getting sick. The point is, if I change coordinates, I get the same thing back again. If I write it in UV, I can convert it to A and B by the usual substitution theorem. That determinant, the Jacobian factor, comes up here. Now, I do need to know that the reparameterization, it doesn't change the orientation. So like that's something that's needed. But if you have a orientation-preserving reparameterization, then you can prove, in fact, that the flux is the same no matter which parameterization you calculate it with respect to. However, if you flip the normal, if you trade your normal for minus the normal, then the flux changes by a sign. That's this. It's again that. It's an oriented integral. Now, in contrast, the integral with respect to the surface area element isn't oriented, right? Like surface area, what's the surface area of a sphere which is positively oriented? What's the surface area of a sphere which is negatively oriented, right? It doesn't care whether it's the normal's pointing in or out. The surface area is the same, But flux cares about which side is up. Kind of like your bank account, right? Like there's a difference between a withdrawal and a deposit, right? The bank is well aware of this. They won't let you confuse the two. They're quite well oriented on this issue. It's true. Okay, so hey, here's our first standard example, the sphere. I worked that out for you today. All right? I've collected them all here in a convenient list for you. Here's a sphere of radius r. The right circular cylinder, taking z as the axis, thank you, Zach, has this vector surface area element. There's the scalar surface area element. Here's the surface area of a little finite cylinder. Nothing too surprising there. The cone, I did not work that out today, but it's simple enough to see how you do it. The cone is what? You have a fixed spherical angle phi naught, right? So the spherical coordinate phi is frozen out. You use rho and theta as coordinates on the cone. And so the spherical coordinates naturally suggests this parameterization, x equals to rho cosine theta sine phi naught, y equals to rho sine theta sine phi naught, z equals to rho cosine phi naught. That gives me this parameterization of the cone. I calculate the coordinate, the partial velocities. I take the cross product, and I get this fantastic normal vector field, rho sine phi naught phi hat. It's so wonderful. These simple surfaces which are built from freezing one of the coordinates, whichever coordinate they freeze, they will take that coordinate's hat as the direction of the normal vector field. Like the cone is phi equal to a constant, right? So the normal to it is the gradient of that level surface, which is just phi hat. Very geometrically natural, this result. So there's the ds for the cone at angle phi naught. That's nice to know. If I ask you a question about flux through a cone, you don't have to derive this. You can use this. That saves you this calculation. Although you got to know what it's built over, right? Because you have to be able to plug these parametric formulas into the vector field to make sense of this formula. So it's not for the uninitiated. If you have a plane containing vectors a and b and base point r naught, well, this is kind of a simple case, but this is important to physics. In fact, oftentimes in physics, if you're asked about the flux of a vector field through something, more often than not, it's the flux of a vector field through a plane. In that case, you just take the vector field, you dot it with the normal to the plane, and you multiply by the area of the little planar segment, whatever that is, and that gives you the flux. It's the simple, basic case of flux, really. And so for a plane which contains vectors a and b, you just take a cross b. That gives you the normal times du dv. I mean, it's just simple as that. And so to calculate the flux, well, of course, the area is given by that, but whatever. And then there's the graph example. Talk about that. All right, some examples. Make it bigger here. All right, there we go. So example 7.6.3, I say calculate the total mass of a sphere which has mass density inverse tangent of y over x. That's weird. Of course that's theta, right? Probably the reason for that. Okay, anyway, so the point here is that the mass per unit per surface area element, mass per surface area is sigma. So dm is sigma ds. If I want to find the total mass, I just integrate sigma ds over the surface. So right, yeah. Well, the ds, of course, is r squared sine phi d theta, right? Sigma is exactly just theta, because that's what inverse tangent of y over x is in terms of spherical coordinates, right? So 4 pi squared r squared. All right, there's an example. Calculate the average of z squared over the circular cylinder. X squared plus y squared equals to r squared. Okay, so how do you calculate average over a surface? What should you do? You integrate the thing over the surface, right, and divide by the surface area to be fair. Just like in Calculus 1, to calculate the average of a function, we integrate from a to b, we divide by b minus a to be fair, right? So you have to divide, you have to weight by the sort of bulk geometric content of the object, in this case, surface area. Surface area of the cylinder is 2 pi RL, and then I just have to integrate z squared over ds, but that is simple enough. Let's see here. Z is actually a parameter on this, right? So z just stays z. Like if I plug in, if the formula for z is z, if the density, if the formula is z squared, I just leave z squared alone. There's no parameterization to plug in. I mean, we actually had to work a little bit to understand that sigma was equal to theta here, right? That required a little bit of an intuitive leap, right? Here, z just stays z squared, but then r d theta dz, we derived that a little bit earlier today for the cylinder. And then you integrate and you get that. Okay, so that's the notion of an average. How about a centroid? Find the centroid of a cone. Here it is. The centroid of a cone, the pi over 4 cone, well, of course, so here's the definitions, right? 1 over the surface area of the cone, integrate x over the surface. 1 over the area of the surface, integrate y over the surface, integrate z over the surface. Of course, it's a cone, right? So by symmetry, you immediately know, yeah, which is the x bar and y bar are 0, right? Because the cone has that z-axis in the middle. It's clear the centroid has to be on the z-axis, everything else being equal. So we immediately know that x bar and y bar are 0 by symmetry. So I, just a little bit earlier, calculated that the surface area of a cone was pi r squared times the sine of the angle. So sine of pi over 4 is 1 over root 2. 1 over root 2 is root 2. That's why there's a root 2 here. So this is the 1 divided by surface area. And let's see here, where is this coming from? This is the surface area element, remember? Maybe you don't remember. Just a second ago here, I derived that for the cone, ds is rho sine phi naught d theta d rho phi hat. Of course, we could look at this because we're not doing a flux integral at the moment. We're just calculating surface area integral. So this being pi over 4, it gives us rho over root 2. Let me jump back to the example. So that's why that's rho over root 2. That's this whole thing is my ds, right? And then z, why is z? What's this here? That's z, right? Z is equal to rho cosine phi naught. But cosine phi naught is cosine of pi over 4, which again is 1 over root 2. So this is Z in spherical coordinates. And so I get r times the square root of 2 over 3. And there you go. The centroid is at 0, 0, r square root of 2 over 3. Yeah, Luke?
Just to clarify, this is the shell of a cone.
Right, yeah, this is not the solid cone. This is just exactly just a conical shell, right? There's the moment of inertia with respect to the z-axis. In other words, if I was to take that conical shell, right, and if I was to spin it with angular velocity omega about the z-axis, how much kinetic energy would it have? Well, that's described by this moment of inertia. I omega squared would give the kinetic energy if I put in the appropriate mass factors and such. So this has to do with how much kinetic energy is contained in a conical shell that's spinning around the z-axis. That's what that calculation has meaning with. All right, so there's the graph example. Goodness gracious. I promise these examples are nothing to sneeze at. Don't misconstrue my comments. So, I heard Zach with that. So there's some examples here, right? And then that gets us to Stokes Theorem. Now, I'm not going to cover all these examples in class. They're there for you to read. Basically, these are gory examples where I have, here's a vector field, here's some annoying surface. Like this one is really annoying. This is a closed cylinder. It's got the side, it's got the top cap, it's got the base cap, and you got to calculate the flux through each one separately and add them together. And so that gives us 3 different integrals we have to add together to get the net flux. There's good news. On Thursday, we're going to learn Stokes Theorem and the Divergence Theorem. And the wonderful thing about these theorems is sometimes, just sometimes, they'll allow us to actually avoid calculating the flux and trade it for the integral of like a volume integral. They're just, it's much like Green's theorem. They sometimes are helpful. This can't be avoided. I'm not showing you this vacuously. This